Okay, question 7 is a simple harmonic motion question, and it's a relatively straightforward one. So just make sure you read the question carefully, and in the end they're just giving us this expression for the resultant vertical force, and it depends on the displacement x in the following way, and we can see that the net force, and therefore also the acceleration, is directly proportional to the displacement and opposite to it. So that's what we usually have to write when we have to sort of outline why SHM occurs. So we can say because the net force and therefore the acceleration is proportional and opposite to the displacement. There you go. So they normally give you 2 marks for these questions, where you have to remember that you both have to mention proportional and opposite. Opposite gives you the 2nd mark, but for some reason in this question they are only giving you 1 mark. And I think looking at the mark scheme, it seems like it's enough to just write proportional, but sometimes they mark you down if you forget to write opposite as well. So that's pretty important. Then they want us to work out the angular frequency, omega, of the oscillation. And you have to remember that the acceleration in simple harmonic motion is always negative omega squared times the displacement. So whatever coefficient is in front of x when you write it in terms, a in terms of x, that's going to be omega squared. So let's just do that. I've got the net force, so divide by mass on both sides, and then you're going to get this times x, and from this we can see that omega squared is going to be rho a g over m, which means that omega is square root rho a g over m, and they give us all those values. We have the mass, we have the cross-sectional area, we know what g is, and the density they also give us. So let's just plug in the numbers. 1.03, 10 to the 3 is pay attention to units, of course. You never know if you have to convert something. Times 9.81. Divided by the mass, 118, and that's in kilograms, and the density was in kilograms. So okay, everything works out well, and we do also get the right value, 4.43 radians per second, which is approximately 4.4. Then we need to work out the maximum kinetic energy. They tell us that it was initially pushed down this distance. Okay, so this is of course the amplitude that they give us, the maximum displacement from equilibrium, and it's good they give us that because we have to remember that the maximum speed when the object whizzes past the equilibrium, then that's omega amplitude. It's called the amplitude x naught here. So omega amplitude is always the maximum speed, and we can use that to work out the maximum kinetic energy, because we know Ke max is half m v max squared. So half m times omega amplitude squared. So we know the mass was 118 kgs, omega was 4.4. And then now we get 0.250. I have to square all that, and we get roughly 71 joules. Okay, and then we have to draw a graph of the kinetic energy. And again, quite simple, right? I mean, I would just be a little bit careful that we can see we can say when time is 0, say it's at its maximum displacement, sort of this positive value, and that means, of course, if I were to graph the position curve, I get a cosine, which means the velocity would give me a negative sign, and the kinetic energy would therefore be a sine squared, right? So I have to graph a sine squared function, and I know what that looks like. It starts off at 0 because that's when we let go at the maximum displacement, where it has 0 instantaneous velocity, but then it's going to reach a maximum sort of after a quarter of a period, and then after half a period it's down at the other maximum displacement, and then of course then it goes back again, and as it whizzes past equilibrium has maximum kinetic energy again, and then back to its starting point at maximum displacement from equilibrium, where it has 0 kinetic energy. There you go, relatively straightforward problem.